My name is Vitaly, and I'm going to talk a little bit about so-called ngZRAM, new generation ZRAM, which is like an initiative, a possible substitution for the existing ZRAM implementation. So we'll cover what that is and what the substitution will be, and the current work and obstacles that we have come across so far doing that. I've been working with embedded Linux on the C side, indeed, from like more than 20 years ago, for Mona Vista Europe, Philips NXP, and eventually moving to Sweden for Sony Ericsson, Sony, and whatnot, and now work in Malmo and have like smaller subsidiary of the bigger company called Consulco, which is US-based, and doing consultancy services on behalf of this Consulco AB, the Swedish entity. In this presentation, I'll give a brief overview of Linux swapping because this is like a necessary background. We can absolutely skip it if you want, because maybe you all know about this. Maybe you know about this better than me. That's a possibility. So everything is skippable. But anyway, the the initial intent is to give an overview about Linux swapping in a nutshell, and about ZRAM and what it is, and how it operates, and why we may want to have a substitution for it, and what the substitution is going to be about, and then some words about moving forward and the possible contributions that maybe you guys would want to do. Yeah. So Linux swapping, well, we all know pretty much every Linux system nowadays, including embedded systems even, is using swapping technique, where you have pages that are rarely used, and we push these pages out of RAM to save on RAM, basically to gain some space. And now with the RAM prices skyrocketing, that's also a good thing to have, right? So what we do by swapping, or another term for this is paging, is we use secondary storage, which is larger. It's usually solid state or flash device or I don't know, whatnot. And we store the pages there. So we save memory by pushing these pages out, and on demand, there's an exception generated, and these pages are being put back into RAM for use by CPU or GPU or whatever caused the exception of not having this page. So we use MMU capabilities in a pretty straightforward way to do this. And by doing this, we, in a sense, trade memory for performance, because the secondary storage is usually slower than the primary storage. So what we can do also to sort of mitigate that is we can use RAM to cache swapped out pages, and that will be killing the purpose, basically, if we don't do a special trick of compressing the pages that are being swapped out, because, well, the thing is, they're not used, so we can compress them, and we can decompress them basically in the same way as we would upload them from the secondary storage. So we trade performance for memory in a sense, but we gain flexibility by doing that. So this is still a sensible operation. And here is where this compression thing comes into play. So we compress pages on swap out to save on RAM, and some data pages, and we do swap out data pages. Really, we don't swap out text pages, the code pages. We swap out data pages, and they're usually very good at being compressed. So what we need also is we need some kind of allocator that is good of densely storing pages that have been compressed, because normal allocators are dealing either with the sizes of one page and above, or with some predefined very small sizes, like we have kmalloc caches for instance, 64 bytes, 128 bytes, and so on and so forth, but they're bound to power of 2 values, and they do not approximate well the compressed object, for instance, of a size 514 bytes. So we need to have something more flexible to be able to densely store compressed pages. So what we have is thus a front-end and back-end architecture where we have compression back-end, which compresses the pages, and we have allocation back-end, which is used to allocate memory, allocate RAM to store the objects of some odd sizes in a manner that we're actually saving on RAM. So ngZRAM is used for this purpose with a bit of a different flavor, because it's actually a RAM disk. So it's not a swap means per se, but it is used as a backup storage. So it's an emulated block device, and it's used as a backup storage for swapping on many Android devices. I think pretty much on all Android devices. But basically, what it is, it's just a RAM disk, but not an ordinary RAM disk, but a RAM disk with compression, and it's operating on pages. So it's written a RAM disk on steroids. That's what I wrote, but maybe it's just the opposite. It's not steroids. It's, I don't know. RAM disk on inflators or deflators, whatever. So in fact, it's a very simple thing. ngZRAM is a simple thing. It has a block device interface, so it's using this whole submit BIO interface, which is no surprise. So for read and write operations, and it transforms these operations to read, decompress, and return data in case of the read operation. And if it's a write operation, then it still has to read in most cases. It still has to read a page, uncompress it, modify the data, compress again, write back. So really, it's a simple thing, right? However, if we take a look at the current state of things in the Linux kernel, so I counted like a couple of weeks ago, we can say that, well, I mean, no offense, but it's a bit bloated, right? For this particular purpose, which doesn't seem to be a huge, rocket science type of thing, we have 5,000 lines of code, which constitute like 170K. So that's probably a bit too much, maybe. And if we look closer into this, we can see that, of course, I mean it's nicely written. It's a good proven by time software. I absolutely. Sorry.
It's totally not. It's a piece of shit. And you shouldn't just not be using it, but also not replacing it, because it's replaced by the protection store less version of ZSwap that's integrated in the swap layer that swap the other executives work on.
Uh,
That's not actually correct, because if you don't have any backing storage.
Well, as I said, the backend store less ZSwap that's currently landing upstream is part of the giant swap array.
Yeah, we have been discussing this for a real long time, but the thing is that I'm not covering it that much in this particular presentation. But the thing is that Android vendors are very keen on keeping ZRAM. So making I don't know, a huge phone manufacturer known by the name of S, or another known by the name of M, switch from using ZRAM with all the parameters and bells and whistles that they're using to a completely different thing without, at least currently, those bells and whistles. This is an impossible task as of now. This one. Yeah. It's on.
Let's see. Let's put it that way. Like 2 weeks ago, all the file system and memory management developers met in Zagreb, and there were big sessions on swap. And the swap maintainers, including the one working for Google and the one working for an Android device vendor, and a bunch of people from other Android device vendors, all agreed on that path forward. It's going to take a while. It's not going to instantly happen. But the common agreement is that ZRAM as a swap backend, not as a compressed RAM disk you might need for something else, is on the way out and is not going to keep the weird special hooks in the swapping code just for it, because they're really painful both for the MM and the block layer.
Yeah, I totally agree. I totally agree. And then again, there's a certain overhead with especially write operations if you do the via ZRAM. I totally agree. But still there is some sense in substituting ZRAM and not just kicking it out, in my opinion. But yeah, let's continue. But I absolutely understand your opinion, and for the specific purpose of swapping, ZSwap is definitely better. ZRAM, it's still proven by time, and I believe it's a good driver. But for the purpose named before, this seems like quite a bit of an overkill. And there are projects looking for a leaner alternative, and that doesn't necessarily mean only Android vendors. Just as a small illustration, it's also from a working system. So these are the parameters that are there in sysblock ZRAM that we can use for various configurations. And that's very nice that it's so flexible. But once again, you need quite a bit of time and background knowledge to understand what these parameters are about. So maybe we can get away with something simpler, hopefully. And this is where ngZRAM comes into the picture. And this is the initiative to create a slimmed down version of ZRAM. And since once again we want to do something new and modern, it's very important that it should be written from scratch, and the focus should be on simplicity and performance. And well, if we're good, then it might eventually replace ZRAM if accepted and if it has proven itself viable. We are not in that position yet. But then the second thing was that the idea or the push from my side was to implement this potential ZRAM replacement in Rust for a bunch of reasons. And well, memory safety is one of the reasons. We all know Rust is not the silver bullet, but still there's a benefit because it does prevent, I would say statistically, about 80% of the bugs related to memory mismanagement. Rust has fascinated me once, like 2 years ago. In a sense, I'm still fascinated. It's a good fit for system development. I did some experiments implementing same things in Rust and in C. Some kernel drivers, some toy kernel drivers, or not so toy kernel drivers, and the outcome was that performance-wise, on average, Rust versions weren't worse. So sometimes they were worse, sometimes they were better. So for some things that you can express well in Rust, you not only get the benefit of having better memory safety, but sometimes you get also benefit on having a better performance. Then again, since ZRAM is configurable in so many ways, it's cool. It would be cool if we had it in a modular way. And Rust encourages modularity, so that's also something that speaks in favor of it. And there's also this why not? Let's try an experiment type of point. And yeah, why not? If we start from scratch, why not really start from scratch? And if we try to re-implement ZRAM in C, like it's implemented, then we have a bigger chance of just ending up, doing a carbon copy or copy paste from several places. And this is something that I would like to avoid. So, what do we have to do? We need to implement a ZRAM, a RAM block device. So it's a block device with compression, and we need to use the block device API that's already there in Rust. So it needs to register itself in the system via that interface, and it needs to interact with a compression backend and with an allocation backend, because this whole block device thing acts as a front end to compressor and to allocator. And here's where we can have some issues, really, even by looking at this, because there are no bindings ready either for compression backend or for allocation backend. But if we start doing things, well, there are all not that many examples of block device drivers. They're already in the kernel, but there's our null, the null block device, authored by Andreas. And basically, what we did, we took the inspiration. So just using the R null and transforming it into not null Rust block device is something that we started on. So it's this cube processing that we modified. It's nowhere near the code that I could show here, so I'm not showing it. So this is the excerpt from Andreas's driver to sort of give an idea where the modifications take place. But also here we have some obstacles with regard to performance, because if we do it like the very very good Rust way, using q_rq, so q request, we seem to have some performance hits compared to the ZRAM implementation, and from what I understand, it's because we don't use the direct callbacks from block device operations as ZRAM does, because the Gen disk builder does not provide the option of doing that. And I think it's the memory safety that is the reason behind this. But maybe we at some point need to tweak this and regain the opportunity of using the submit bio like the ZRAM driver does. It's something that has to be considered. Yeah.
You can add that. I didn't need it, so I didn't add it. Just not implemented yet.
Yeah. But is there like a memory safety consideration behind this, or is it just you don't need it, so you don't?
I just didn't get to it.
Okay. Yeah. So maybe we'll consider this in a how should I put it, more thorough way. So that was the first thing. So performance, we need to watch it. Next thing, as noted, allocation backend bindings are absent. So we have basically three options. We can create bindings for ZS malloc and use it pretty much in the way ZRAM does, but via one more layer of indirection. The second option is we can use the allocation backend called ZBlock, which is written in Rust, so we can use it directly, but it's not in mainline yet. And yeah, and it's probably IAM who should take the blame, because it's mostly written by me, and I really didn't have much time retrying to submit and merge it to the mainline during the last 4 months, because I was also consumed with something else. But anyway, we can do that, but it's becoming a bit of a problem because too much stuff becomes like out of tree stuff. So right now the toy ngZRAM implementation is just using the standard kernel allocator, which is not a good thing because it doesn't provide the density that we want eventually. But for a prototype, it's still okay. So it's the bullet number 3 that is currently used, but it's not going to be like this in the end. Compression backend. Well, there's no good way as of now to do this, because the crypto API that the Linux kernel is using for all the compressors is nowhere near having a binding in Rust. So this is something that someone has to do. And since it's a relatively complex API, this is not going to happen tomorrow. So what's been done is the direct out-of-tree non-mergeable binding for ZSTD, because ZSTD is the most popular compressor right now, both for ZRAM and ZSwap. So we just did a direct binding for ZSTD, which is, again, not nice. But then we have something to work with. We have some functional prototype instead of a non-functional prototype. So this is, of course, a temporary solution, as I said, to keep things going. And since we don't know what the compressor API would look like, or will look like in future, there may be quite some work to change this ZSTD binding to the real API when it arrives. So there's an effort to be done anyway. But once again, life is life. We can comfort ourselves by saying that we're on the bleeding edge of the technology. And yeah, then you have to sacrifice something for it. Yeah, so that's basically it. The way forward, as I see it, is first of all, crypto API mapping, the bindings for crypto API should be implemented in Rust. This has to happen anyway at some point. It's not only the ngZRAM that is a potential user of it. It's a huge part of the kernel, and we need it. Resume that block submission attempts. It's tempting, not only because I wrote it, but also because when a piece of code written in Rust interacts with another piece of code written in Rust, then we increase memory safety and decrease complexity, as opposed to having to create a specific binding for the C code, which also inevitably increases the amount of unsafe pieces in the Rust code. So add real compression to ngZRAM when the crypto API is there. Well, testing and profiling, the boring part, and mainline submission. So, well, that's a bit of a wishful thinking, but this is what we want to do in foreseeable future. And it would be absolutely awesome if anyone is interested in contributing to this. So please contact me. Or Andreas, for that matter. I think Andreas is also interested, but also has a lot of things to do on his plate. But when it comes to block devices in Rust, he can probably give a better guidance than me. So please contact either me or him, or both. And thanks for your attention. I don't think I see the mic, but if there are any questions.
Hans?
Oh, yes, I think it is. No, can you turn it around? No? No, it says it's on. I mean.
No, I changed it, but it has a problem with that antenna. Don't throw this, please. Yeah.
Just don't throw it.
It is more how we use it in production. So we actually use the ngZRAM together with swap as a swap device, and it works horribly.
Sorry?
I work for a large company. We have a lot of servers. So we actually use the combination of swap and ngZRAM, and it works really badly because it also has bad interactions with the out-of-memory killer. So the system always thinks it has more memory, and it never kills any process. So we actually call it brownouts, because the server will be like in a bad memory state for more than half an hour or something, and everything will be slow and horrible because the bad interaction between ngZRAM and swap and the memory model. So we're actually looking at changing away from that and using, what's it called, ZSwap, that Christoph recommended.
Yeah, in case you don't need a block device and you don't have any historical reasons, if you only want optimized swapping with compression, ZSwap is the way to go.
But what's the limitations of can we easily do the change just changing to ZSwap? There was some limitation about having a backing device, or
As of now, there is, yes.
But can I still use some of the part of the memory for ZSwap, or I cannot?
Well, I think you can currently already configure ZSwap to actually not do any write backs So it just becomes full. It still requires the backing swap device, because otherwise the configuration is invalid. But then you can probably use a null block device for that. So I think it's a valid in the current kernel. I think it's a valid combination. I'm not like I cannot commit to that, but I think it's a valid combination.
Yeah, thanks.
Any more questions? All right, thanks again.
Thank you.